Hi everyone, welcome again. So let's get started. Now, this session will be very exciting because that's what you're waiting for, the research field from our faculties. So individual faculties will come here in the podium and they'll present their research topics and discuss a little bit more. But remember, this is not the everything that they do. We have a wonderful poster session in the afternoon. So if you do have any question, you should also reach them out in the poster session, as well as plenty of time that we have during the breaks and lunch. Okay, so we don't expect much questions right now because it's just very short lightning talks. So I'll invite Gang first, who will be giving the talk. Now remember, the faculties who are giving the talk, you have to press right arrow in this laptop so that the next speaker appears in the screen, while you have this clicker you can use for moving these slides. Okay, thank you very much. You're already.
Is this PowerPoint or PDF?
Yeah, this is PDF thing.
Okay.
But this will work in PDF.
Okay. Good morning. So I'm Gang. I'm going to introduce my research. Apparently, you see the left and the right doesn't match, right? So I have been here 16 years. I have done a lot of research in different areas. You know, computer science is moving fast. I'm pivoting my research. I have different focus of different years. This morning, one student approached me, want to know my networking research I did. Unfortunately, it's not even put here or here. Okay, so right now, my focus is really on, can you see the red dot? Okay, on computing for healthcare. We're doing innovation, right? I'm going to create a new whole field within computer science, of course, in collaboration with other science like healthcare. So computer science, I think we embrace innovation. I'm going to talk about this topic, what types of research, and how, as a student, you can participate in publication in terms of journal and conference as well. I thought about all this. Okay, I will give you one example topic research which is ongoing. This is a research not from National Science Foundation, but from National Institute of Health, because we're doing healthcare. And it is computing or computer, right? You do see some computing device. You see the smartphone, right? That's kind of mobile computing here. You see some wearable device that could be the ubiquitous computing here I'm talking about. So my research group actually designed this wearable hardware and get a company to manufacture it. So basically we have the accelerometer gyroscope minimized and put it wearable on your ankle. So for patients with Parkinson's disease, so I want to make sure first I'm working on a significant problem. In addition that we have very novel science. The problem is that patients with Parkinson's disease, about 50 of them have freezing of gait, and that don't have a cure. So freezing of gait is that the brain or neuron sometimes get disconnected with their muscles. They want to move their head and keep walking, but their head cannot be lifted off the ground. So basically get stuck. And while they keep moving on the upper body, they will fall. And this could happen 1 time per week, 1 time per day, or 10 times per day. When it comes to case you have multiple times per day, basically your life sucks. So I phone interviewed many patients. They're willing to pay whatever they have if they can get off from this freezing gait. So it's pretty significant problem. Now, the computing science or computer science we have is that it's on the wearable, ubiquitous, and mobile computing. We design wearable solutions, and we also put in AI, machine learning, into it to analyze the digital signal from the sensors 24/7. We analyze the digital signal stream, use digital signal processing algorithms, AIs, to say, hey, is this an intentional stop? The patient just stopped walking, or this is a freeze. They want to walk but get stuck. How to abort it? So we have to do that within 0.0 seconds, at most 1 second, because if it's later than that, even though you detect it, you cannot do anything. They're going to 4. So we have this vibration device. It's something similar like the vibration on your smartphone, right? We make it wearable so that once we identify it gets stuck on the freezing of gate, we trigger a vibration with a specific frequency and strength at length so that your neural system of your brain can be distracted. Somehow your muscle can follow what you're thinking. You can lift your feet and keep walking. So we have tested this with over 20 patients in the past 3 years. And my PhD student, Kelly Coleman, has been working on that. And now Johnny Clapham is joining that. And we're also in commercialization phase right now. We just started a company. A student is temporarily pausing PhD status and become Windermere staff to focus on the commercialization for the following 15 months. And he's still working on PhD. He will finish that. Okay, so this is just one example. We have hardware, we have digital signal processing, we have machine learning, we have application, we have system deployment. We even have user study. So some of the kind stuff probably will help in the future. We have some new hire of a faculty member we're collaborating with. Okay, another one also with health, also with the hospital, Parkinson's Disease Center in Richmond. So it's about a tremor. Parkinson's disease patient has a lot of symptoms. Freezing of gait is just one of them. They also have tremor. The hand will involuntarily vibrate. We'll also use our device. You see, this is a convolutional neural network to detect when it happens and what's the degree, how serious it is, things like that. And you say, develop wearable and also mobile API and apps based on the API. So we just do everything in the whole system ecosystem. These are just examples of my research. I will not have time to go more, but give you a bigger picture. So what I'm talking about. So on the bottom, you see, my group design sensor platforms. We do design hardware if we cannot find existing hardware on the market. If we cannot, we design it. So far, you see, we designed a lot, like this wearable for freezing of gait. We also have electromagnetic sensors. We designed use microcontroller wearable, and based on that to detect the angles of your joints when you're doing motion. We also have textile sensors, basically for some material like Levi, the gyms, they have some, and other industries, they have some material you can wear, but it's conductive and stretchable. When you stretch, the resistance level will change. We use a microcontroller, cut off one piece of the fabric and weave it with a special machine on the t-shirt you're wearing. And right now it's on the knees, on the knee sleeves. We use that to measure how your ankle bend 24/7. We use that to help diagnose potential diseases or progress of knee arthritis. We work with doctors that have X-ray, MRI. We connect all the sensors together. So, and also this one is that we design some hardware to measure AC power and DC power for Internet of Things device deployed in the hospital environment to say what's the power consumption and say what are they doing, what is they exposed to do. Or the power consumption shows that they get compromised, they're leaking data, privacy or security, those issues. So basically, based on the application on the top, I put it example applications. Basically, the application mostly come beyond the computer science. Almost all my collaborators, not computer scientists. They're from School of Medicine, School of Nursing. So the problem came from them, their existing health problems. And we identify how we can design, use wearable hardware or anything else to help conquer that. Of course, in between, beyond the application and the sensor platform, I'm going to focus on how do you do modeling and how do you do system, right? The modeling, I apply machine learning, digital signal health to build a convolutional layer or transformer, or even right now, large language model, how to fine tune it to solve the problem, basically. That's a key. And also work on the system side to look at, okay, for the computing system, here is not a server computer. mostly it's a phone or even a wearable device. How the AI models can work in that environment to be energy efficient, computational efficient, meet the delay requirement, and other things. Okay, to advertise that this area, we have to create journals, create conferences so students can participate. So I'm currently editor-in-chief together with Yanfu Li from University of Pennsylvania on this SM transactions on computing for healthcare. It was starting 2018. It's a new journal, but it's one of the top journals. You can see this journal is beyond incorporating computer science, but also have ECE, mechanical engineering, biomedical, psychology, and health in general. So the whole editorial board consists of a lot of faculty from different areas. But it is computing for healthcare. So basically, we're bringing the impact. We're advancing computing, but to benefit healthcare as well. So it's in nature interdisciplinary. Another one is for conference. From 2016, I started to help build a conference called Chase. So this year, Chase was invited to be part of ACM FCRC. FCRC typically will choose multiple topics to think they're interested to emphasize per year. And this year, they picked 10 areas, and it's in health, computing for health. So our Chase conference is picked it as a conference to present that. So just to let you know, a lot of things are ongoing, and we'll keep pushing new research areas as well. Thank you.
Hello, everyone. My name is Jie Ren. I am an assistant professor here. I joined William & Mary from 2002. So I would like to briefly introduce my research, which is democratizing the big application deployment on computing systems. So nowadays, we have a lot of big applications, such as this scientific simulation, the machine learning and the artificial intelligence, and a lot of in-memory databases. Those applications are extremely resource consuming, not only just the computing resource, but also the memory resource. So the big memory can help to achieve all those goals. In terms of the deployment process, the scientists or the software developments, they have their data, they build their solutions, but finally they need to deploy on the computing resources. And in terms of the computing resources, currently it comes to a lot of heterogeneity here. In terms of the computation, we have the CPU, we have the GPU, we have the specialized accelerators such as TPU or like FPGA to accelerating the computing. In terms of the memory resources, we have the traditional DRAM, we have the high bandwidth memory, we have the persistent memory, and we can also access the cloud storage resources. The increasing heterogeneity actually increase the management complexity of the existing solutions. So my work is focusing on the new abstraction, new algorithm, and new software system to democratize the big application deployment for the data management and system standpoint. So here I would like to emphasize what's the democratization mean here. So I talk about it from two perspectives. From the system perspective, we want to lower the computation resource cost in terms of the purchasing those hardware or the energy perspective. And also we want to democratize the human efforts when the people trying to deploy the application onto this heterogeneous computing platform, so that the programmer can use just a simple API to use the entire all the resources without significantly changing their applications. So here is some example what I am doing. I am working on the enabling the billion scale machine learning model training on those GPU clusters, such as those large language model, transformer based, or the deep learning recommendation model. And I'm also working on enable the large-scale scientific simulation to working on the heterogeneous memory systems. Here we can see some HPC applications such as molecular dynamics or particle in cells, they are requiring a lot of memory resources. But on the hardware side, we have the memory hierarchy, so how to use them together to make it run fast and efficient. That is what I'm doing. And besides, I'm also working on the machine learning for the computer system optimization, such as we are using the anomaly detection to trying to find the anomalies in HPC clusters. We are trying to predict the memory access pattern so that we can have a better intelligent caching algorithm, and also understanding the log from the system using the large language model. So if you are interested, please reach out with me for my William Mary email. Yeah.
Hello, everyone. Can you hear me? Okay. It's so weird that they have two monitors. Okay. So I'm a new professor here as an assistant professor, and I graduated from Georgia Tech in focus on human-computer interaction or human-centered computing. I will just briefly overview some of my research area. One is, of course, HCI, and I just want to know who has heard of this term HCI. Raise your hand. I was really surprised. So basically, HCI is a field that I really care about human beings, right? As compared to some other, more traditional CS faculty members here, and maybe some of their research cares about or focus on speed, accuracy. But my research really cares about how human beings interact with the system in the real world situations. And while after we are interacting with all the systems, what are the perceptions change or not, and how that influence people's behaviors. So this is my research area. And historically we have all computers. So this is basically a computer, right? But later on we have human AI interaction and a human large language model interaction. So which also combines different areas, but it's still human-centered computing. And another research thread is my work is also focused on data visualization and also social media analysis and social computing. We're all living in a social media and social networking, space. So and how our speech and behaviors are influenced by the social media influencers. So this also misinformation. This is also my part of my research. As well as cognition learning. I will talk more about more concrete examples under my current research focus on cognitive learning, CS education, and programming languages learning. Basically my whole dissertation actually during my PhD at Georgia Tech is focused on trust and trustworthy. So if you have, look at the news this week and, the president actually, they have an executive order focused on what? The safety and the trustworthiness of the AI and also the large language model. So I think there's a lot of huge opportunity to explore how can we ensure, more equitable access and also the responsible use of AI and large language models. As well as my research also focuses on equity. So what does equity mean in computational science or in computing? So how many people have used ChatGPT? Quite a few, right? So, but if you look at the Pew Research Center data, the PEW is basically they were usually run the national representative sample. So if you look at the most recent poll, and only 19% of the US population have used ChatGPT. So my question is actually, who are not accessing to the most recent technologies? So those are the people we need to help, right? So this is more about the equity and accessible in terms of computation and computing. In terms of the domain or a lot of design applications, in my field is mostly focused on health. We'll talk about what kind of health domains I've been working on, and also crisis informatics such as disasters and crisis management. COVID-19 is one of the special public health crises. So, okay, several, my ongoing research is just to highlight one. There are many other areas that we're working on. So one is what I call is human large language model interaction. So, okay, instead of just talking about which model, these days the BERT or GPT and who performs better in terms of what task, and I care about what are the people needs, values, and activities in the case of using large language models, right? And how people use ChatGPT in your writing, your assignment. Are you allowed to use that? And also, how can we ensure the ethical use and deployment of large language models, and also to establish this kind of standards to their trustworthiness in different contexts? And also, how do people's interactions with large language-based or enabled system impact their perceptions and behaviors? So as one of control example that we are currently doing evaluation of field deployment regarding how large language models or enabled systems, in terms of mentoring students, learning programming and CS education, as well as we're also designing tools and games to promote AI literacy. This is what I call a generative AI literacy. So if you ask, the key is around surrounding you, and how do they trust, Google or any AI enabled systems? Probably yes. Maybe they are the golden truth or the ground truth, but is that necessarily the truth? So this is something you really focus on the educational aspect to the K-12, for example, and also more advanced users, even some of the professors in other departments, right? And also to examine the ethical use and deployment of large language models and establish standards of their trustworthiness. We're also deploying different kind of benchmarks to what we mean by trustworthy large language models. And also another areas is really promising from my perspective, is to really engage with the community-based research. So this is basically a very HCI classic methodology to engage with local communities, with the people you care about, in producing more applicable and usable and trustworthy of the tools. So this is one example that this is our very recent paper that also got best paper honor. I mentioned in the top tier conference HCI that we are trying to understand how large language model generate misinformation compared to the human created misinformation. And we've actually found that the AI generated misinformation, they tend to be more simulating the human tongue. There are more findings related to this work. I'm happy to talk more offline. Well, in terms of how we adopt this human-centered design and evaluation in different domains of the applications, I've been working on different health-related areas, ranging from chronic illness management like diabetes, and also public health, like, of course, COVID-19 is one of them. And also recently I've been working with, different researchers and across different areas in addressing people's mental health, asking about how much isolations we have done in the past few years. We lost so many years, we want to get them back. As well as, focusing on caregivers and children, as well as, and also prevention, such as healthy eating and the physical activities. So for that, I will end my presentation. And remember, the one thing we care about is not just to focus on the accuracy and speed, but also how we can adopt this human-centered computational science in addressing the real-world situation and contexts. Thank you.
Hello, all. I'm Yanfu Zhang, assistant professor in computer science, and I started my appointment this year, so I'm quite new here. So my research is about machine learning on graphs. Actually, graph is a generic term which can be used to describe a lot of different applications. So here we have some examples. For example, social network. If you are using Twitter, Facebook, or maybe LinkedIn, actually every user is a node, and every maybe follow or unfollow is just some kind of interaction, and we can view that as some kind of edges. So in that sense, we can build this social network as a general graph. Also, we may have like information networks. For example, if we want to read a paper and we want to organize our thoughts about that paper, maybe we can draw something like that. So that's kind of like a knowledge graph, or maybe just simple information networks. Another example here, road network. So this is a little different from previous one because here every destination may be a spot in this graph, and we are interested in like the distance between different destinations. So we can schedule our paths if we want to reach out to a specific spot. Also, we may have Internet of Things, which basically every sensor, every equipment is a node here, and they have different data. They have different requirement for the throughput. So here we can again build the connection between different equipment, and then we build this whole graph. Also, brain networks, basically we parcel brains into different regions, and different regions have connections. They exchange signals, so we can monitor their signals in different area, and then we can build this whole brain connector. Also for protein interactions, so that is very useful if we want to annotate the function of new proteins, or maybe just to infer the possible interaction, which is undiscovered here. So we can see, actually, as a general term, we can use graph to describe all these kind of things. And actually, that is where machine learning comes into play. So traditionally, if we want to do some applications with images or with texts, we can use many established algorithms, such as from XNet to very closely VIT or something. And for large language model, we have generative models such as BERT, STM, and GPT. So that is for images and text. And actually, we can see a connection between images and text and the graphs. So image actually is a regular graph. So every node has exactly, I don't know, based on the definition, based on the dimension of images, basically it has like 4 adjacent pixels, right? And for text, we can use like random field or like conditional random field. That is, we can we can evaluate the probability that two words comes together, and use that probability as some kind of connection. So even in this case, we can generalize the texts and the images to a more general graph setting. In this simpler setting, for texts and images, definitely we can use this established methods. But if we generalize to graphs, we must consider more. Besides node classification, where in the classical image case, it is more like we classify what does some image represent. We may have some more applications such as link prediction. So previously, I mentioned that social network. So link prediction here means that we want to find some new friend for a user, and we might want to recommend some new product to a user. So for community detection, we can use that to detect some induced graph from induced subgraph from a large graph, and that can be an essential structure of that graph, and we can use that to do a lot of predictions, particularly for like brain connectors. So here we can find the difference. In previous methods, we are dealing with regular data structure, but in graphs, every structure is irregular. So we do not know how many neighbors one node may have, and how many graphs we may have, how many nodes each graph has. So that in that case, graph deep learning on graph basically is to deal with this irregularity. And previously, we have many different classic methods to solve all these problems related to graphs, such as we can use a spectral graph theory. We can use discrete structure to design some quite smart but very difficult algorithm. A recent new trend is we can unify everything into a graph neural network. So it is not universal, but it can address a lot of problems. And we can see evolution here from very ancient version graph convolution network, which derived from graph Fourier transform, to a very recent version based on like attention or based on transformer. Actually, my research is about is following this stream, and we can do a lot of things based on the current evolution of graph neural networks. For example, you can looking for stronger expressive power. For that reason, since graph Fourier transform is defined on all frequency domain, but previously, typically graph neural network only can be considered as a low pass filter. So that is something we can improve, right? And also, we can extend the current research on graphs to multimodality. For example, we can consider the combination of graphs and text. We can consider how to inject the knowledge automatically into graphs. So based on that kind of method, we can design automatic method to derive a knowledge graph. And we can also consider fairness for graphs. So for social networks, maybe resources are distributed unevenly across users. So it is important to make this kind of consideration. So more generally here, we can consider like machine learning for social good, for science, and for health. So if any of you are interested in my research, maybe we can have some talk after this lightning talk, and you can find my contact through the webpage in the computer science department. So that's my presentation.
Hi, my name is Stephen Herwig. My name is Stephen Herwig. I'm an assistant professor. I've been at William & Mary for about a year now. And my research area is system security. So what is systems? Well, systems is a low-level software that applications run on top of. It includes the operating system, the network protocols, the storage stacks, all of which provide services to applications for interacting with their environment. What happens if that environment is untrustworthy? Well, think about it. It probably is. We run our applications on third-party providers like the cloud, which share and sell our data and expose it to hackers. We run sensitive banking and messaging applications on our phones, which we misplace and lose. And there are all sorts of emerging fields, some of which we've already heard about today, things like IoT, smart vehicles, and embeddables, where an application's environment is a set of ever-changing peers, some of which misbehave. So my overarching research question is, can systems protect applications from untrusted environments? And in approaching this question, I use two broad techniques, special hardware and cryptography. The main type of special hardware that I use, which is available on many new CPUs, is called secure hardware enclaves. The main property that enclaves provide is memory isolation. So while an application is running in an enclave, its memory is encrypted, and only the CPU can decrypt that. So this is very powerful because in theory, all the other parts of the system, like the co-resident applications, the other hardware, even a physical attacker can't observe or interfere with that enclave. And I'm sure you're familiar with cryptography as a way to hide communication. But nowadays, we use cryptography to solve very complex problems, like computing on encrypted data, sharing that data at a very fine-grained, with very fine-grained permissions, and then allowing anonymous access to that data. So to give a flavor of this research, I want to briefly describe one project that my group is working on, which combines both techniques. And the setting here is the cloud. So imagine we have a bunch of clients that are sharing some cloud storage. Now, so this could be something like Amazon's S3. So they want Amazon to store the data for them, but not actually see the data. So to do this, all the clients share a key and encrypt their data and then upload it to the cloud. But there's two problems with this. The first is that given enough time, the cloud or some determined attacker could brute force that encryption key. And the second problem is that an attacker could hack one of the clients and get the key. So how can we mitigate against this? Well, it's simple. We simply periodically rotate the encryption key and re-encrypt the data. How can we do this efficiently? Well, this is what my group is looking at. So we're taking some ideas from secure messaging apps, things like Signal, and combining them with enclaves to provide really efficient group key establishment protocols. And then rather than have the cloud actually re-encrypt the data for us, we're using a technique called proxy re-encrypt. Rather than have the clients re-encrypt the data, we're having the cloud do it for us using a technique called proxy re-encryption. So this is a really cool technique where the cloud can re-encrypt the data in place without learning the new encryption key. And I want to underscore that we're really building this system. So we're modifying the Amazon SDKs so that we can evaluate this system on the live cloud. So in this talk, I've briefly touched on my research, which is designing and building secure distributed systems using secure hardware and applied cryptography. You can find out more about my research at the link below, and I look forward to meeting you throughout the day. Thank you.
Hello, everyone. This is Bin Ren. I'm an associate professor at William and Mary. And my research focuses on the parallel computing and high-performance computing. And my recent research focuses on the accelerating the deep learning and deep neural networks on resource-constrained devices. And today I'm going to introduce some of my recent research. And if you are interested in this, and contact me, and we are hiring, and hopefully we can collaborate in the future. Okay. So today I'm going to introduce real-time deep neural network execution on mobile devices with compiler optimizations. Okay. So first, let's look at some very general background. As we all know, these days deep learning and deep neural networks are everywhere, and these are just some sample applications, and many faculty members in our departments are working on different kinds of fields and different kinds of applications. And usually we can execute these kinds of applications on different kinds of hardwares like GPUs and FPGAs and TPUs. And all of these hardwares are deployed either on the server or on the edge side. And my research, recent research actually focused on the edge side, focused on the mobile devices. And why we want to focus on the mobile devices? Actually, because of three clear advantages. The first one is about the privacy. And for many times, if you take a picture, if you want to do some analysis, if you have a video, but we don't want to upload this kind of data to the server because of some privacy issue, privacy concern. And yeah. Then if you have the AI capability on your cell phone, then that's great. Yeah, you can just run the AI capability and deep neural network analysis and capability on your cell phone. And the second one actually is about the latency. If you upload the data and do the analysis and get the result back, the network communication will incur significant latency on the overall procedure. Yeah. And the third one actually is about the cost, especially the cost for the vendors. And if vendors want to run their AI capability, usually if they can run this kind of AI capability on your cell phone, then they can save a lot of money. They can save the money on their server, save the money for the cloud. Yeah. So these are three clear advantages for running the AI or deep neural networks on mobile devices. However, it's challenging. Yeah. Although these days our mobile devices are very powerful, we have cell phones with CPUs, GPUs, DSPs, very powerful. But our deep neural networks are also becoming very large. Yeah. So for example, if you want to run YOLO object detection on cell phone, and it usually takes millions, hundreds of million seconds. However, if you want to achieve the real-time processing, then it usually needs 30 milliseconds or 30 frames per second in this kind of speed. So there is still a huge gap between them. Then how to address this? This is a research, my recent research focus on. So actually here are just some samples, okay? So I can briefly introduce both of them. Actually, the first one is compression and compilation co-design, and the second one is a pure system method. And in the first one, actually, probably we have very straightforward thinking here. The model is large. Why not we just compress it? Yeah. So we just prune it and compress it in the smaller one. This is very correct thinking. And there are lots of research focused on this aspect. For example, we can prune the model, and we have different kinds of pruning approaches. If we categorize these pruning approaches into two categories, then we have the regular, the structured pruning, and we have the non-structured pruning. The non-structured pruning can prune the weights in a very random way, but we can preserve the model accuracy very well. And however, the pruned model is very hardware unfriendly. If we want to run this model, it's very challenging for us to get the ideal performance. For the structured pruning, we can get a very dense, very structured model, but the model accuracy will be sacrificed. So can we do something in the middle? yeah, this is our research. Yeah, we can do. Yeah, of course, we can design some fine-grained structures and very small, patterns, and we can organize the computation and the communications, around this kind of patterns, and we can design the, proper pruning approach and design the proper, compilation optimizations around this kind of design. Then we can get both high accuracy and high performance. So this is a very brief introduction about my first, approach. But we still have a very clear downside here. We need to compress the model, we need to train the model, we need to retrain the model. So it's a kind of intrusive method. Yeah. So a very straightforward question here is, can we do it with a non-intrusive method without changing the model at all? The answer is yes. We can use some, pure system approach. We found these days the deep neural networks have lots of layers, have 1,000 layers. And if we have lots of layers, we have lots of, data movement, we have insufficient parallelism. Why not we just, do some optimizations on this aspect? Yeah. So the very straightforward idea is we can just do some fusion. And we fuse some operators together. Of course, we have thousands of operators. Which operators can be fused together? How to fuse them together? All of these are open questions, and this work actually is about this aspect. Okay, so build on all of these kind of techniques, and we designed a deep neural network acceleration framework, and then we can achieve the real-time real-time execution support for DNN on mobile devices for the first time. Our software outperforms the Google's product, outperforms Facebook's product, outperforms many open source tools. If you want to contribute to this kind of work, and please contact me. Okay, if you are very interested in the system aspect of the deep neural network or deep learning acceleration, please contact me. And we are hiring. And yeah, thank you.
Hey everyone, finally it's my time to introduce myself. My name is Pradeep Kumar. I'm assistant professor in the department. And I'm going to present very interesting insight on the deep learning is systems research for data science. And what we do, when you talk to some systems researcher, you will definitely get an idea. Our job is to improve the performance, but the performance is just a metric. We all do improve the performance. But we also care about other aspects of the system. We want to provide fault tolerance, usability, productivity, programmability, and many other metrics. Let's take some idea. When we do that, what exactly we do, we advance the understanding of the system and establish new abstraction theory and technique. Now, the second point I want to emphasize a lot. When you buy today a USB device, you simply put it in your laptop and boom, everything accessible. You don't need to know about the hardware internals. You don't need to know about the software that makes it accessible to the user. So that's what the system research is. And that's why I usually define systems research is building an abstraction so that the complexity is fully hidden to the end user. Right? Now, why is that very much important? Because when we provide such kind of simplicity to the user, the complexity is transferred from the user to the systems researcher. So we literally deal with lots of the complexity in research ideas. And you might simply think, oh, this is already done, but may not be done because we need to make it very easy to program, very easy to use. Now, let me just give you one idea. Right? People have built operating system for years and years, and there's still some research to be done. Now, what are the new things that we can do for deep learning? One of the research challenge that everyone knows is deep learning training is not only just memory hungry, but it is also computational heavy. That everyone knows. Now, what we can do, right? We can, at least our team believes, that we can introduce sparsity in the model as well as sparse data both. And that's where the future is. When we talk about the pruning that been just discussed, we reduce the size of the model parameter by almost 10 times 50 times, things like that. We have achieved sparsity up to 90%. So a billion model parameter can easily fit in maybe just 10 million data points, right? But in order to achieve that, you see some of the patterns that are introduced. Well, these are the patterns. And anytime you have the pattern which is slightly different than the model which is dense, we don't have any programmability of the system. System usability is lost completely. There are no libraries, there are no usability at all. And of course, you won't be able to get the performance simply because you remove these parameters. Almost impossible. Rather, we have papers saying that these models take similar amount of time that the dense model takes. And that's what the research area is here. Now, one of the more interesting research idea here is inspired from operating systems research. The operating system does provide the usability of the underlying devices to the user without introducing much overhead. Now, when we are able to remove so many parameters, these becomes very tiny models. And it can run quickly because we are developing algorithms to make them really, really fast. Now, because of these models have become so fast, the overhead that the framework introduces, like PyTorch or TensorFlow, is becoming very noticeable. And believe me, no researcher really knows about that. We just measured this a couple of months back and show that when your model becomes very small, it is no more determined by the GPU runtime, but it is because of how much time PyTorch or TensorFlow takes to run on the CPU, because the overhead runs on a CPU and it only runs on a single thread CPU. So they are not even utilizing the CPU. So those are the new insights that systems researchers always come up with, like me, and try to find out the solution. So definitely, system support is what we are working on. Algorithmic support we also need to work on because libraries are absent, such as NVIDIA don't really support all the sparsity kernel that we need. And then parallelizing is really, really hard. Now, once we do that, our job is to come with a solution that is more deployable and advances the knowledge that we need to know, right? To make people aware about the underlying system. So we have developed a whole new framework where sparsity is actually first-class citizen. You can easily program by introducing sparsity to your data or to your model without worrying about much of the details. Now, this is backed by some of the optimized sparse kernel, which we have only taken care so far for sparse data called GNN1. We understand their patterns and show that these patterns actually are same across different sparse kernels, and just optimize one, and you can actually optimize all of them. That's again what the systems researchers usually do. Now, some of the works we are already focusing on is introduce sparsity in the model. We have great success so far. We just haven't published yet. We are exploring sampling to make the data small, another interesting research area that we are focusing on, and introduce some lower bits to do the computation. So rather than using 32-bit floating point, let's use 16-bit floating point. And we'll gather some more speed up there and many more. We have a poster session. You all are welcome. So because system research is very hard, we place a lot of emphasis on mentoring people. And believe me, all of you have some experience with deep learning, but when people come and talk to me, they simply say, oh, this is too much. This is where I start working, and my research area is actually below that stack, below that software stack. So they are usually not very well trained on system. Sometimes also because university do not have a mandatory course on operating system, it's purely optional. So we really don't find a student. But if you're interested, our group spend considerable time on training them. And it is very satisfying. At the end of couple of years, they say, yes, this is the job I would love to do. I would make the life easier for the rest of the people, and I'll take all the complexity myself, right? These are my student. I've been very fortunate to work with them. First three are already here. Sarah is not here. But actually, my first paper came with Sarah, so she's very special student from me. So that's all from my side. And we have just, if you have any question, you can definitely talk to me. But just an announcement, aside from this, we have canceled the break. So I would like to request the next speaker, Dennis, here, while we switch the slides.
Thank you, Joe. Can you hear me? So again, my name is Poshyvanyk. Since I already gave a talk, I'll try to be brief. My area of research is software engineering in maintenance. My core research interest is in applications of machine learning to software engineering, but I also collaborate with other faculty in the department. I collaborate with Adwait Netkarni on projects related at the intersection of security and software engineering, and also with Chaparro, bug reporting, and legal aspects of software engineering. Just talking about machine learning for software engineering, obviously everybody knows GitHub Copilot here, very effective tool, which is based on neural large language models. So actually, we started researching this area in 2014, believe it or not. We've been using neural language models for software engineering tasks a long way before this became cool. At that time, actually, our papers got rejected. People were like telling us, you don't know what you're doing and it has no future. Well, I mean, we've been persistent. And as I told in my earlier slides, persistence is important. And that's the opportunity to do things that some people don't agree with you with. So two major research directions here, deep learning for software engineering. That's what we've been currently working on for good 9 years or so. We're leveraging deep learning to automate software engineering tasks. And recently, we've been also tapping into trying to understand how we're going to build these systems of the future, where deep learning is going to be an essential component in the systems. And I'm not going to delve into details, but there are lots of really interesting, unique, and difficult challenges to overcome how we build and maintain these kind of systems. And again, we've been covering pretty much solutions spanning all software development lifecycle, from requirements to design, implementation, testing, and maintenance. These are just some example solutions that we've developed, which rely on deep learning and domain-specific analysis. In particular, program repair, bug reporting, test case generation, clone detection, and code reviews. So I just want to quickly mention one specific area that I'm going to skip all this, that we are currently focusing on. And it actually relates to understanding what these models are capable of learning from the training data. And some of you may have heard about this paper, which basically showed that Copilot was generating security vulnerabilities, right? And suddenly, and again, we are in this honeymoon phase where we're just applying these language models for everything without even paying attention to what these models are generating. But eventually, we will start paying attention when these kind of security vulnerabilities will make it into production code. So we actually trying to design techniques to try to understand what these models are actually learning from training data. And I have my students here, David, Alejandro, Daniel, who've been bravely advancing this very challenging area. It actually involves a lot of math. And so we actually been using causal theory to try to explain what the model was able to learn from the training data in terms of the concepts that you as programmers understand, and how to use that knowledge to effectively debug these models or test these models, or how to improve these models. And there's a lot of really cool work which is currently happening in this lab. Some of this work is fairly foundational. Hopefully, once this is done, we're gonna move into applications. So I see these guys, they can't wait to start moving into application phase. But again, lots of exciting opportunities, and we are really excited. So hopefully see you around in my classes, and hopefully, research projects down the road. So thank you.
Hello, everyone. My name is Sidi. I graduated from Wayne State University in Detroit, Michigan, and I just joined the department as an assistant professor this fall. So today I prepared 2 slides. One slide is mainly discussing my primary research direction called vehicle computing. And on the second slide, I will mainly talk about my additional research direction, edge intelligence. So for the first one, vehicle computing. Basically, my research topics are more related to the emerging mobility systems, like the autonomous driving, connected cars, electric car, as well as emerging software-defined vehicles. And we know like vehicles are normally served as the transportation tool in the past century. However, with the rapid development of the communication and onboard computing, vehicles are not served as the merely the transportation anymore. In addition, they will serve as the computing. Basically, on this slide, we can say like vehicles can support the smart home sensors, public safety cameras, that they can send the data to the surrounding vehicles and to support the computation-intensive tasks. So this shows some examples of the computation role of the vehicles. However, vehicle computing not just limited to the computation. Vehicle itself is also a mobile communication platforms. For example, as shown in this figure, we can say the vehicles are normally communicate with the road infrastructures, like the traffic lights, as well as the signal tower, to receive the global information and perform more advanced computation tasks. And we also have the term such as a vehicle to everything, vehicle to vehicle, as well as a vehicle to grid, which is related to the energy delivery function of the vehicles. Think about the electrical vehicles. When some disaster happens and there is no electricity, actually the electrical vehicles parked in your home, at your home, or in the manufacturer, they can also deliver the electricity back to the grid. And this is also a promising use cases about the electrical vehicles, not just limited to the energy efficiency. And the fourth function of the vehicle is also related to the sensing, because vehicles are normally equipped with a myriad of the sensors, like the cameras, LiDAR, and radars. So they are capturing the surrounding information. And we will think the vehicle itself as advanced mobile sensors, which can be used to continuously capture the surrounding information and to support the other analysis, like the path planning, like the bridge health monitoring, etc. And then we will also think about the storage function of the vehicles. Like for the autonomous vehicles, every 8 hours of driving, it will generate around 40 terabytes of data. Absolutely, we cannot send all those data to the edge server, to the roadside unit. We need to clean the data, do some data synchronization, and then storage the data. So this is also another research topics or research challenges that we would like to address. So basically, this slide shows the 4-tier vehicle computing paradigm, shows the vehicles will communicate with IoT, like the drones, scooters, this kind called the micro-mobility systems. And also it will communicate with the surrounding vehicles, collaborate with the road infrastructures, even communicate with the cloud to support different applications related to the computation, communication, storage, energy delivery, as well as the sensing tasks. And my additional research direction is related to edge intelligence. So how many of you have heard about the edge computing? Cool. So edge refers to the edge of the internet, like your mobile phone, your laptop, also some smartwatch are both the edge devices. Normally they are small in size and have very limited computation power. So like due to the rapid development of the edge device, we do not always need to rely on the cloud. So for the cloud computing, normally we need to push the data from the data source to the remote data sensors to deal with the data. However, due to the latency, bandwidth, as well as a privacy issue, and also some as an end user, we hope the application be more personalized. So due to those requirements, we do not always need to push the data to the cloud computing. Instead, we need to deal with the data near the data source. So that is also one case of the edge computing. The edge intelligence here aims to solve the mismatch problem between the edge with the AI algorithms. Because normally the AI algorithms were developed by the very, very powerful cloud data centers. So there is a mismatch problem and we would like to address. So we currently will also focus on the collaboration between vehicles and between edge and edge, as well as some collaborations between the cloud and edge. So it can also support different applications like the connected health, smart home, smart manufacturing, and public safety monitoring, as well as AR or VR on the glasses or even for the autonomous driving. It can be treated as an emerging tech lake to support the new applications. So far, you can say like my research is not like it is more like the problem driving based. And currently we have a close collaborations with 3 automotive companies like the Toyota, General Motors, and Ford. Both collaborate with the research lab to solve some real-world applications problems. And also it is an interdisciplinary research area. So I do welcome students from different disciplines to join the lab, and we can talk later offline. Thank you.
Hello, everyone. My name is Ashley Gao. I am a new assistant professor in the Department of Computer Science. I graduated with a PhD from University of Virginia this May. So like some other faculties that just gave the presentation were very new here. So today my topic will be about domain generalization for healthcare. So how many of you have heard about domain adaptation / domain generalization? Okay, so some of you do, some of you don't. So basically, domain generalization is a topic that deals with the fundamental problem with machine learning, or in the current era, let's say deep learning. Because machine learning / deep learning algorithms, when they are trained, you train them on the data set. And then you say, okay, I am applying this newly trained algorithm on a practical case. And then you find out that in practice, your machine learning algorithm does not perform so well as it did on your training. Why? It's because there is something called the distribution shift between your training and your testing. So let's say you train your samples, you train your classifier, let's say as a transformer, on data set with people from one ethnicity. And then you apply the same transformer model for people of different ethnicity. Then in this case, your model might not perform so well based on the features that it has learned to prioritize during its training. And the same feature, when it's applied to the testing data, are not so pronounced. So they are no longer the guiding feature for your classification or prediction anymore. So the point of domain generalization is that we would like to build a system for previously unseen data set given one or multiple training data set. So in this image, you can say we want to classify bicycles, right? So we have bicycles from we have pictures of bicycles from a very clean background. And then we have pictures of bicycles taken from the hallway, which is a different domain. So let's call it blank domain. This is hallway domain. And then we have the corner domain where bicycles are parked in the corner. And so how do we learn from those 3 fields / domains to summarize the essence of bicycleness? Therefore, we can classify and previously unseen domains bicycles correctly, right? So this domain let's call it colorful corner, right? This domain is different from all 3 domains, but we would like to do some classifier training so that this classifier, even though it hasn't seen this domain previously, is still going to perform well. So how do we make sure the domain, so how do we make sure the classifiers perform well on previously unseen distribution, right? Okay, so now I would like to make a announcement or make a distinction between the traditional without domain adaptation or domain mitigation strategy, with domain adaptation strategy, and with domain generalization strategy. So if you see the first picture, so what do we mean by all the colors, right? So let's see, let's look at the blue one here. So the blue one is saying I have a distribution, which is my blue samples, and it's a binary, data set. So I have positive samples being the circles or dots, and then negative samples being the stars. So if I'm training a deep learning based classifier, then so my classifier make a decision boundary with this dotted line. So for this data set, it's doing a perfect job, right? It's correctly classifying all the positive samples on one side of the dotted line and all the negative samples on the other side of the dotted line. Okay, so that's all good. But then let's see you have a similar domain, which this is the yellow domain. You also have the positive and negative samples of the same classes, but see the distribution here is slightly shifted, right? So the yellow things distribution and then the blue things distribution laid out in this 2-dimensional picture are different. So now if you still are gonna apply the same classifier for this yellow domain, then you see that it's not doing as well, right? It's classifying a lot of negative samples to be positive, and then but it's correctly classifying the 2 negative samples correctly. But the gist of the story is that if you have a deep learning based classifier and you don't do any domain shift mitigation strategy, it's not very likely that it's guaranteed for your classifier to work well on a different but similar domain with respect to domain shift. So domain shift is the difference between your training domain or training set and your testing domain or testing set. The training and testing domains must be similar, right? Otherwise, it doesn't make sense to apply the same classifier, of course, with domain mitigation. So similarly, we have the blue and the red domains here in this picture. And this classifier is performing very poorly on both the red and blue domains. So that's the problem with deep learning based algorithm without domain mitigation. Now, I mentioned one strategy of domain mitigation is called domain adaptation. So the domain adaptation strategies assumes that you know the distribution for your target domain. So you only look at 2 domains. So you have the blue domain for your training, and you have your you have some part of the yellow domain for your training, and you would like to correctly classify yellow domains data. So there are multiples, like not million maybe, but let's say there are like hundreds of strategies to do domain adaptation to align those 2 domains. Like in this case, where the 2 domains are aligned by various ways, such as adversarial domain alignment. So the negative samples and the positive samples are now correctly distributed on the both sides of the decision boundary. So this is for domain adaptation, in which you are working well on the target domain, but the assumption is that you know some of your target domain's information. But let's say, okay, it's working on this target domain, which is yellow, but it's still not working. It's still not very robust because it doesn't work on the red and blue domains, right? Even though the red and blue domains are the same question, are proposing the same question to be classified or predicted. So that brings us to domain generalization, in which we have 4 domains, and you see they are now. Let's see, we know the 3, the blue, yellow, and green domains. So they're perfectly aligned, and so we would like to find a way to also align this unknown target domain in such a way that if you build a classifier on these 3 domains knowledge, you can extract the essence of what makes the positive samples different from the negative samples, so that this classifier will work universally, well, mostly universally, on a previously unseen domain with different with a different distribution. Okay, now this brings us to for healthcare, right? You have a algorithm already, so you would like to so the algorithm's purpose is always to be applied in a realistic setting. So let's see, you have 3 patients, and then each patient has several data. So each of the have several data points. So each of those things are 3 domains belonging to 3 patients. Now, the problem that I have been working on is how do you develop a classifier knowing the data from the purple patient and the blue patient, and you want to make it work on the yellow patient without previously knowing anything of the yellow patient. Because when you're deploying a strategy, you don't usually know your test subject before you deploy it. So that is the end of my talk. And if you're interested in domain adaptation, especially in the sense of general domain adaptation and generalization for healthcare, please come and talk to me. Thank you.
Yeah, hello everyone. My name is Huajie Shao, and my research focus lies in machine learning and federated learning for large language models. So I think large language model is a buzzword, but when we train the large language model, we should collect a lot of data from different users. So it may has a risk of data privacy leakage issue. So federated learning is a new distributed learning paradigm that can collaboratively train the machine learning models without sharing the data with a central server. So it can protect the data privacy of users. So there are some challenges that we need to address. The first one is the data heterogeneity, because we collect data from different users or different hospitals. They may have different heterogeneous data. So how can we aggregate data to improve the performance of the large language model? And secondly, when we do federated learning, we should transmit the model parameters from the local clients to the central server. So it may result in the communication cost and energy consumption because of autonomous model parameters. So how can we use like a few shot or one shot federated learning to reduce the communication cost and energy consumption? And also, how can we develop some privacy preserving algorithms to protect data? And also, yeah, my advisor told me that, if you are working on the large language model, you give credit to OpenAI. So I should do something differently. So currently, I'm working on a foundation model for internet traffic. So starting from this March, we are pre-training a 0.2 billion large models for internet traffic. So last Friday, we already finished the pre-train of the foundation models. So we also did some tasks on 2 downstream tasks in network tasks. One is the DOH attack detection. Another is DOH query generated detection. So its accuracy is very good. For the downstream, its accuracy is over 98%. It means that in the future, I don't need to rely on OpenAI for their large language model. I can use my own model for the future research project. The second one, I'm also working on the physics sky machine learning. So the goal of physics sky machine learning is to incorporate the physical laws into the machine learning to improve the interpretability and generalization. So there are a couple of challenges. So first of all, how can you discover the invariant physical law? For example, we have multiple different domains, like Newton's law. So for Newton's law, it can be applied to different domains, like on Earth or on the moon. But for the deep neural network, it will overfit on the data set collected in the current domain. It cannot generalize to another domain. So how can we incorporate the invariant physical law into the machine learning to improve the generalization ability? So here, actually, I submitted 3 NSF proposals. One proposal collaborating with Stanford, Caltech, and Berkeley. It's an AI for Astronomy Science Center, $20 million, Another is the physics guide machine learning for cyber-physical system. It is $7 million. And also we get one funded from the CPS. It's a medium proposal. So yeah, I think, yeah, this is my, introduction of my research project. If you are interested, please feel free, talk to me. Thank you.
Okay, so I'm Yifan. This is my 4th year as an assistant professor. So I basically work on the direction of computer architecture and a little bit on the data visualization side. So I consider myself, or I brand myself as building explainable computer architectures. So what is explainable computer architectures and what is computer architecture? And as you have seen that a lot of our faculties have been working on algorithms and machine learning, but without chips, we cannot really efficiently run these algorithms. So my goal is to design chips. And we see modern hardware is getting larger and larger. We have this distributed computing. We have these wafer scale computing devices. That is, this single chip is as big as my face. So they are really getting large scale, and we have these multi-GPU systems. We want to use multi-GPU systems to improve the performance, and GPU is actually an enabler of deep neural network algorithms. And we also have this type of actuators that are being interconnected together to deliver the extreme performance. And systems are getting more and more complex, like this type of SoC systems, as this is an Apple M1 chip. So they provide really high heterogeneity to deliver high performance. So we really have problems like as the scale and complexity are getting larger, is we cannot really fully understand this type of problem. So if we cannot understand this problem, then we cannot really design efficient architectures. Then we can have functional bugs, performance problems, security and reliability problems. Like one critical example is Spectre and Meltdown. That these problems are, these systems are designed in 1980s, but the problem was found in 2008. So at 30 years, nobody really fully understands this system. Then eventually we have this problem that costs billions of dollars that we need to patch these problems. So what if we design this problem that the designer can understand at the beginning, right? So that's my goal. So as you know, I work on a specific direction called simulation, because we design chips, we cannot really manufacture those chips. Those are super expensive, like AMD, Intel, NVIDIA. They spend billions of dollars working with TSMC to produce this type of chips. I cannot produce this type of chips. So I build simulators that recreate the behavior of these chips to simulate or mimic the behavior of these chips. So if we change some parameters and we change the design, we can see how the behavior changes in the simulators. And also, I've already talked about the computer architecture side, and because we also care about the human perspective, because eventually humans are the designers of those chips. So we really have to understand or consider if human can understand these type of systems or not. So we developed simulators like GPU Sim, which is the first simulator that is specialized for multi-GPU simulation. It provides high flexibility, high performance, and high accuracy. And we provide things like we really care about the usability of this type too. So we developed something called Akita RTM. We care about real-time monitoring, that we can look into the black box of the simulator and discover problems without waiting for the result to come out like 24 hours or a few days later. And we also develop visualization tools, as I have described before. And then we basically require a lot of JavaScript and TypeScript, HTML, CSS skills to develop this type of visualization tools to see how this hardware executes in the simulator, how performance changes, and what exactly this hardware is doing at every time moment. So we develop this type of tools to help developers understand what's going on. And so I would say, why work with me? Then I would say, working with me, then you're not only going to publish in top tier conference, and you're also going to have a lot of collaboration opportunities. And you are going to develop our skills, including software development, web development, and data visualization. Although I design hardware, I really care about software development skills, that you are going to work with large scale open source software. And opportunities, you will have opportunity to do internship at major companies, and I have connections with startup companies and large companies, and I can always give you job recommendation. And I would say, as a PhD, how I define a graduate PhD is that you have an opinion. For example, my opinion is that we care about human perspective on chip design, and I want my graduate PhD to have an opinion, and you have the capability and the leadership to lead this direction. Okay, I think that's all my talk. I should still have Oscar, right?
All right, thank you. Two more talks, guys. I believe everybody wants to have lunch, right? So I'll try to be very brief. Oscar Chaparro, assistant professor here at the department. I lead the software evolution and analysis lab. These are my PhD students. I'm very fortunate to have them. Very smart here, very smart, and I see some of them are here, so that's great. Our research goal is to assist developers in evolving, designing, maintaining, and testing large software systems. We want to make them high quality. And for that, we propose different techniques that combine machine learning, natural language processing, code analysis, and so on, that can help developers on that end. And we also promote or design methodologies, practices, and so on. We're working on different research threads right now. I'm going to briefly summarize some of them. The first one is related to code complexity. So as we know, some code could be really complex to maintain because they have different structures. They are written in convoluted ways. And this makes hard to understand and hard to evolve the code, right? So we are exploring the use of code verification techniques that use formal methods to that end. And these techniques, what they do is they check the code and they produce a report of different types of errors in the code, right? And because they are using formal methods, there are guarantees that that if it detects one bug, that it covers all the bugs in the system, but it produces false positives. And these false positives, well, if we have complex systems, then they will produce, these techniques tend to produce more and false positives. So we actually correlated the number of false positives with how hard it is for humans to understand code, and we found that there is a positive correlation. And the implication of that is that we can use information from verification tools and use AI to try to predict when code is harder to understand or easier to understand, basically when code is complex, right? So we are exploring the use of AI to that end. And well, my student Adishan, I see him there, so he's working on this project and he's gonna present this project during the poster session. Come and talk to him to know more about this project. And we are also exploring the use of automated refactoring that can simplify the code, and our approach is to use verification tools to that end. We want to minimize the number of false positives, and that, according to the correlation we found, that will lead to simpler code and easier to understand code. The second research thread that we're working on, that I want to talk about here, is related to the software supply chain. And some students are working on this project. They're here. And essentially, well, probably you have developed software, and the first thing we do is use open source projects, right? Open source packages. We use them all the time to build software rapidly so that we don't have to reinvent the wheel. Of course, there are challenges associated with them. We need to keep track of them, of the dependencies. We need to comply with their licenses. We need to manage vulnerabilities that may come out. And also, we want to comply with regulations from the government and other entities. So one important technology that have come into place to that end is software bill of materials, which basically they are machine-readable documents that list all the dependencies of your system. And there could be like thousands if you have a very large software system, right? And they also would help with license tracking and security vulnerability tracking. So we conducted a study with many open source projects and people that work on machine learning, cyber physical systems, and we identified that this technology is not yet mature. And for many reasons, I'm not going to talk about all these reasons, but one of them is, well, lack of tool support that can accurately produce SBOMs. So that they are complete, they're accurate, they can, they have the right information for developers to address the challenges. And we're exploring the use of AI to produce SBOMs that are usable, that are effective, complete, and accurate. Trevor, my PhD student, worked on this area, and he will present again during the poster session. So come to him and talk to him about this topic if you want to know more. And well, we are also working on licensing, so how to do license compliance. And one of the main actors in doing license compliance is lawyers themselves. A lot of researchers have explored developers, what are the challenges that they face, but we have explored what are the challenges and the process of license compliance by legal practitioners. And we conducted a study, and we identified different tasks and challenges that they face that we want to address in the future. Nathan is right there, and he will talk more about that during the poster session. And I want to conclude with my last research thread here, which is bug report management. And who has seen these pictures all the time? Right? All of us, probably. And well, some of these bugs actually are okay. I mean, we can live with them in some cases, but for some software systems, it matters a lot. It can have a huge impact on people. For example, at airports, if you have a crash of the booking system or so, that could lead like a huge economical cost, huge impact. So we want to report these bugs when they happen, and actually they are reported in systems that have large use bases, such as Chromium. The other day I went to the issue tracker of this system, and I found that there were more than 100 bug reports submitted that they needed to address. I mean, developers need to address to restore the quality of the software. And well, when they come in, the development team has to go through a lot of steps, right, to deal with these bugs. They need to check if the bug report is okay, it contains all the information. They need to assign it to the right developer who can solve the bug. They have to detect if it's a known bug. They have to replicate the bug, find it in the code, fix it, right? So we have addressed these tasks are very challenging, especially when we have many bug reports coming in. So we have published a few papers on some of these tasks, and we have had the pleasure we have been recognized by the community with some awards as well. And just to give you a very brief idea of what we have done here, we have focused, for example, on developing techniques based on natural language processing, machine learning to detect when bug reports, textual bug reports miss important information, and we prompt the user to provide this information. We have explored also augmenting these bug reports with screenshots of the application of the system so that developers can understand and better the bug and can manage the bug, replicate the problems, etc. And actually, Antu, who is somewhere there, he's working on some of this on this project, so he's also gonna present at the poster session. So come to him. And well, we have explored also the use of chatbots to guide people who really don't have the expertise to report bugs. So with this guidance, it will provide quality verification. It will provide graphical suggestions for reporters to report the bugs. And we have also focused on video-based bug reports, which show graphically through a video how to reproduce the bug and the bug itself. And we have, for example, we have explored the use of deep learning techniques to process automatically the video and try to reproduce it in the development's environment. These are just some of the work that I have done. So of course, there are many more. And if you are interested in all these topics, please come to me and during the breaks or on lunch session. Thank you so much. And last talk is by Andreas.
I don't need this. Thank you, everyone. This is going to be only a 30-minute talk. No. I want to go have lunch. So my research area is in computational science. That is defined over the last 30 years as the intersection of mathematics, computing, and one application area. So as you see, my core here has always been numerical analysis of some sort and high-performance computing. You cannot do numerical analysis without high-performance computing. You can do the other way around, though. I've been dealing with eigenvalue problems all my life, linear systems of equations. Recently, I've been going to nonlinear systems of equations. I've been doing things with discrete mathematics, discrete everything. But at the end of the day, you have to do high-performance computing because the problem sizes that I deal with come from applications. And applications like physics, chemistry, machine learning, kernel learning. To deal with this, you often deal with matrix sizes of hundreds of millions. All right, so your Gaussian elimination doesn't work there. So we've been writing software. We've been collaborating with application domain experts to promote their applications, and at the same time, we promote the core software and core algorithms that we find for these areas. There's a lot of catchy things up there. If you're interested, talk to me afterwards. I'll be here throughout the day. I have several collaborators. These are all over the map, actually, people from numerical analysis, physics. I've been dealing with chemistry for a long time, but recently I've been doing a lot of lattice QCD. This is quantum chromodynamics. I always like this thing. It's just a mouthful. My PhD students, I think they're not here because they work remotely. I have one in Sandia National Labs, another one. Actually, a lot of my students are in national labs. This is one favorite area. So yeah, I think lunch is waiting and I don't want to take this too long. Thank you very much.
Okay, just two more announcements and then we were going to go to lunch. First, not every faculty were able to present. So we do have some other faculties who are here. You should talk to him, especially in cybersecurity. We already have Advait Nadkarni here. You should definitely talk to him. And Dimitri also works in cybersecurity, especially in the hardware side, architecture side. I think he's not here. Peter works on graphics. You should, oh, Dimitri is here. Okay, so you should definitely talk to him. And Peter works on graphics, which we didn't represent today, but he's well-known researcher in the graphics area. Evgenia also didn't present. She works on the system, characterization, and performance. Please talk to her also. And she's our department chair, so you should definitely talk to her. Now, the second announcement is regarding food. We were able to collect lots of data about your test bud, and we use generative AI to have a very nice lunch for you. But in order to know what technology we used, we have reserved chair for the faculty. Talk to them to understand how we are able to do that. Thank you.